Hello, welcome back for Chapter 8. This video is going to contain a lesson for Chapter 8.1. It's all about a single population mean using the normal distribution. So if we kind of go back to what we learned about the sample mean, it's a point estimate for the population mean. So it's a prediction for the population mean. Not really a prediction, it's the mean of just your sample. The sample standard deviation is what we would call the point estimate for the population standard deviation. So we would take the sample and then the standard deviation of that data. A confidence interval is what we're going to work on in Chapter 8. So a confidence interval is another type of estimate, but instead of being just one number, it is an interval of numbers. It provides a range of reasonable values in which we expect the population parameter to fall. There is no guarantee that a given confidence interval does capture the parameter, but there is a predictable probability of success. To construct a confidence interval for a single unknown population mean mu, where the population standard deviation is known, we need the sample mean as an estimate for the population mean, and we need the margin of error. Okay, so 8.1 is when we know the population standard deviation. Okay, so the population standard deviation is known. We need the sample mean or X bar is an estimate, and we need to know the margin of error. So the margin of error is going to be called the EBM for the error bound margin. Error bound margin. The sample mean, X bar, is the point estimate of the unknown population mean. The confidence interval estimate will have this form. So the error bound is what sometimes we call the give or take. So we're going to take the point estimate and we're going to subtract the error bound, and then we're going to take the point estimate and add the error bound. So this would be our lower, and this would be our upper in the confidence interval. So the confidence interval would be the lower and the upper. The lower, the smaller number is always on the left. Let's look at a couple of examples. Suppose we have collected data from a sample. We know the sample mean, but we do not know the mean for the entire population. The sample mean is 7, so the X bar is 7, and the error bound for the mean is 2.5. So the EBM is 2.5. So my confidence interval is 7 minus 2.5, comma 7 plus 2.5. So my confidence interval is 4.5 up to 9.5. Let's look at example 2. Example 2 says, suppose we have data from a sample. The sample mean is 15. Let's write that here. And the error bound for the mean, is 3.2. What is the confidence interval estimate for the population mean? So it would be, the confidence interval estimate would be 15 minus 3.2 and 15 plus 3.2. That's our give or take. So 15 minus 3.2 is 11.8 plus, or comma, 11.8 is the lower, and then the upper is 18.2. So our confidence level is the percentage of samples that are expected to include the true population parameter if you made a confidence interval from each sample. Alpha is going to be the percentage of samples that are expected to not include the true population parameter if you made a confidence interval from each sample. So the confidence level and alpha are complements of each other. And we're going to use this symbol here for alpha. It's this Greek letter. Okay. So here's our formal interpretation of a confidence interval. If you take many samples and make a confidence interval from each one minus alpha times 100%. So our confidence level of the confidence intervals will contain the true value of the population parameter. Our informal interpretation is we are blank % confident that the true population parameter is between blank and blank. And this is, make sure you put a star here, this informal interpretation is what I'm expecting you to use to explain confidence intervals or interpret. We're skipping this bottom piece. So the next page is going to be your instructions on calculating the confidence interval. To construct a confidence interval estimate for an unknown population mean, we need data from a random sample. The steps to construct and interpret the confidence interval are below. So the first thing you're going to do is calculate the sample mean from the sample data. This should be X bar here. Remember, in this section, we already know the population standard deviation. So we already know this. You're going to find the Z-score that corresponds to the confidence level. And we learned how to do this in chapter 7. So we'll go back to that. Then you're going to calculate the error bound for the mean. Then you're going to construct the confidence interval. And then you're going to write a sentence that interprets the estimate in the context of the situation and the problem, i.e., that means to explain what the confidence interval means in the words of the problem. So, calculating the error bound for the mean. The error bound formula for an unknown population mean mu when the population standard deviation sigma is known is as follows. So, we're going to find the Z-score for the alpha and divide that by 2. It's actually the Z of alpha divided by 2 times the population standard deviation divided by the square root of n. And notice this sigma, the standard deviation divided by the square root of n, is the standard error, the adjusted standard deviation that we used back in chapter 7 with our central limit theorem. Okay, so that should look familiar. So it says, constructing the confidence interval. The confidence interval estimate has this form. So we're going to take the population estimate, which would be your sample mean, and subtract the EBM, and then take your sample mean and add the EBM. So the graph gives a picture of the entire situation. So right here. So we're going to be a certain % confident in the shaded area that our true population mean falls between these values. Down here is our lower estimate of the interval, and here is our upper. And so we're predicting with a certain % confidence that our true population mean falls within here. So let's walk through an example that's Example 3 says, suppose scores on exams and statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. Okay, so sigma equals 3. A random sample of 36 scores is taken and gives a sample mean of 68. So we have a random sample of 36, so n is 36. And our sample mean x bar is 68. Find a confidence interval estimate for the population mean exam score. So we want to find a 90% confidence interval for the true population mean of statistics score. So to find the confidence interval, you'll need the sample mean and the error bound of the mean. So our sample mean is 68. And our So we have our sigma is 3, our sample size is 36, and our confidence level is 0.9, it's 90%. So our confidence level is 0.9, so alpha is 1 minus the confidence level, or 0.10. And we have to do alpha divided by 2, which is 0.05. So we are trying to find z of 0.05, where 0.05 is the area to the right. So the area to the right, so if I were to draw this curve here, we're going to have 0.05 area here, and we're going to have 0.05 area here, and we're going to have 0.9 area in the middle. So these have to add to make 1. And a confidence level is always our alpha divided by 2, because we're going to have a tail on the left for the lower bound and a tail on the right for the upper bound. There are a couple ways that you can find this z value, this critical z value. One of them is using inverse norm in your graphing calculator if you have a TI-84, which we have not spent much time on. Okay. You can also use Desmos, and we can also use our formula packet that I gave you. So I'm going to show you all 3. Okay, if you have a TI-84 calculator, I'm going to show you a way that you can use that without going to Desmos, if you'd prefer. So if you hit second in your vars key right here, it will bring up this distribution menu, and you can do your normal CDF that we learned in Desmos in chapter 7. You can do that here, but if you go to inverse norm, and it will automatically come up with your mean at 0 and your standard deviation of 1. A z-score always has mean of 0 and standard deviation of 1. So you just have to put the area, and we want the area of 0.05. Now, if you put in 0.05 and hit paste and hit enter, it's going to give you a negative z-score, because that's the area to the right. And because they're symmetric, the area to the that's the area to the left, I'm sorry, the area to the right is symmetric, and so it's just going to be the positive of that. And that's why you could also put in this 0.95. So if I go up and copy this, and instead of 0.05, I put 0.95, which is the complement, it will give you the positive of that, because they're symmetric. So if you want to use a TI-84 calculator, that's how you do that. That's using inverse norm. I'm going to highlight that here. And so that's how we get this 1.645. Okay. Now, if you want to use in your formula packet that you were given, there's a link to if you want to print this out. It's on the page. It says $2.99, I believe. This whole chart is for the t distribution that we're going to learn in lesson 8.2. But the normal distribution is just this one line right down here for the z-score. You'll see this little z. Now, I suggest you take these areas, these alphas, and write them down below, because this is going to be easier than trying to follow all the way down. So for instance, 0.05 is right here, 0.10, 0.15. Okay, so we were at 0.05, and that's why, notice if I zoom in, right there's your 1.645, because it goes with this alpha, 0.05, 1.645. I'm also going to show you what we learned in chapter 7 in Desmos, so you can also see where we got 1.645 from that. So let's go to Desmos. And I'm just going to copy this for a minute, and then I'm going to, okay. So because we said the mean of a z-score is 0 and the standard deviation is 1, we can put just 0 and 1. And then you can always do, oh, we need the inverse. Inverse of that. So we need the 0 and 1 here. We need the inverse to find our normal curve. And then we do the comma, and then our area goes here. So we want 0.05, and that's why it comes up negative. Or you can put in 1 minus your area to the right, so 1 minus 0.05, and you'll get the positive. So you can put that here. To the right. There we go. Okay. So ours, so you get 1.645. And the cool thing is you can see the graph here. If you were to go up on this graph and put 1.645, 1.6448536, whatever decimals you want to put, you'll see that you're going to get this area 0.05, just like and it will show the area just like we drew right here. This is 0.05 right here. And this is finding a critical value. So I'm going to save that for you, and I'll put the link in Canvas for you to use. Okay. So let's go back to our papers. And now that we are establishing how we're going to find our critical values, I won't be doing on every example, but I'm going to give you some exposure. Okay, so our EBM, our error bound, is found by taking our Z right here, 1.645, times our standard deviation, which should be 3, I typed in the wrong thing here, 3 divided by the square root of 36. Okay, so we are going to go to, you can do this in Desmos if you like. I'm just trying to show you quickly on the graphing calculator. So times 3 divided by the square root of 36. And that's where we get 0.8225. So this is our give or take. So we're going to take our X bar, our sample mean, and subtract our give or take. And then 68, our sample mean, and add our give or take. So this is our lower right here and our upper. So we could say we are 90% confident that the true population mean on statistics exams is between 67.2 and 68.8%, because they were percent scores. So you all are going to score higher than that, I know. Okay, so this is our first one. So take a deep breath. There's lots of parts to it, but we're gonna get some more practice. So let's look at example 2. suppose average pizza delivery times are normally distributed with an unknown population mean and a population standard deviation of 6 minutes. A random sample of 28 pizza delivery restaurants is taken and it has a sample mean delivery time of 36 minutes. Find a 90% confidence interval estimate for the population mean delivery time. So our first step that we learned on the last page is we're going to get our sample mean. We said was 36 minutes. Our population standard deviation was 6, and we have a sample of 28. Okay. Our second is we need to find our critical Z value. Okay, so find critical Z, and we want alpha divided by 2. So alpha is equal to 1 minus your confidence level, which is 1 minus 0.90, which is 10. And so alpha divided by 2 is 0.05. So we want Z of 0.05, which we learned in the last problem is 1.645. So step 3 is calculate error bound of the mean. Okay, and that is found by taking our Z of alpha divided by 2 and multiplying by sigma divided by the square root of n. So this is one whole number here, and that is 1.645 times 6 divided by the square root of 28. And like I said, you can do this in Desmos. You can do it on the graphing calculator. I would not recommend your cell phone. I've mentioned that before this semester because it's easy to press the wrong number. So our error bound margin is 1.974. So step 4 says construct the interval. So our confidence interval is going to be 36 minus 1.974 and 36 plus 1.974. And the cool thing is about a graphing calculator is you can make the calculation and then you can just go up and highlight and it will paste it, and then you can just change that to an addition. So it kind of makes it nice there. So our lower bound is 34.026 and our upper bound is 37.974. And then our interpretation is we are, and you should be writing all of these steps down that I'm working on here. We are 90% confident the true population delivery time for pizza is between, we'll just round to the nearest minute. So 34, and we'll round up to 38 minutes. Now, when you give me the interval, I want the decimal places, 3 to 4 decimal places. But when you're giving me the conversational interpretation, you can round to an appropriate minute. It's fine. Let's look at example 5 here. So example 5 says, the specific absorption absorption rate, SAR, for a cell phone measures the amount of radio frequency energy absorbed by the user's body when using the handset. Every cell phone emits RF energy, and I was just reading about this and how you should keep your cell phone 5 millimeters away from you, because they believe that there's a relationship between having your cell phone too close to your body and body parts, and could possibly a relationship, not causal, but a relationship to cancer. So that's interesting. Different phone models have different SAR measures. To receive certification from the Federal Communications Commission for sale in the US, the SAR level for a cell phone must be no more than 1.6 watts per kilogram. This table below, this isn't necessarily table 8.1, but shows the highest SAR level for a random selection of cell phones models are measured by the FCC. Okay, so some of these are higher than others. It looks like 1.48 is probably the highest that I see on here. A BlackBerry, that was an old one from a while ago. So I'm sure that they're improving, because here the Apple iPhone 4S is the newest one. So this table is slightly old on data. So it's asking us to find a 90% confidence interval for the true population mean of the SARS rates for cell phones. Assume that the population standard deviation is 0.337. So we found the sample mean here of 1.024, and our confidence is 98%. So our alpha is 1 minus that, which is 0.02. So alpha divided by 2 is 0.01. And so you can use your table. You could use, I'm going to show you again on the graphing calculator for anybody that wants to use that. If we go to second and vars and choose inverse norm, and I'm going to put in 0.01, and remember this is going to give me the negative, but we're going to use the positive because it's symmetric. So 2.326. Okay, we can see that on our table as well. So the table is good, but only for alphas that we have given. If we give you a weird one, you won't be able to use the table, but 0.01 right here, and you can see the Z is 2.326 that I'm pointing to, where alpha is 0.01. And you can see in Desmos, we can do the same thing. So it says you need to find Z of 0.01, having the property that the area under the normal density curve to the right of Z is 0.01 and the area is to the left is 0.99. So that's where in Desmos we would put in 0.99 or 1 minus 0.01. You can see here in Desmos how we can find that critical Z value. Putting in area 0.01, 1 minus the 0.01 gives us the positive Z-score of 2.326. And then we can see the rest of our confidence interval here on my paper, where we put in the 2.326 for the error bound of the mean, the standard deviation divided by, the square root of n is 0.1431. So let's look at that on our calculator and just verify. We have 2.326, and then we have 0.337 divided by the square root of 30 is 0.1431, validating that. And your paper should have a square root there. I fixed it. To find the 98% confidence interval, we're going to take the X bar and do plus or minus of that. So there's our sample mean subtracting the EBM and the sample mean adding the EBM. And this is our lower and this is our upper. So we can say we estimate with 98% confidence that the true SAR mean for the population of cell phones in the US is between 0.8809 and 1.1671 watts per kilogram. I'd like you to look at example 6. It says the table shows a different random sampling of 20 cell phone models. Use this data to calculate a 93% confidence interval for the true mean SAR for cell phones certified in the US. And it says it's previously assumed that the population standard deviation is 0.337. So I'd like you to go ahead and put that data in and find your sample mean. And the signal we're going to use is 0.337, and our sample size is 20. And then we can go ahead and find our error bound, our critical Z, because our confidence level is 0.93. So I'll let you get working on that, and then we'll check it together. Okay, so first thing we need to do is find our sample mean and also our critical Z value. So our critical Z value is going to be based on this 0.93 confidence level. So alpha is going to be 1 minus 0.93, which is 0.07. And we need alpha divided by 2. So 0.07 divided by 2 is going to be 0.035. So we need Z of 0.035. And then we'll calculate our error bound of the mean, which is going to be the Z times the standard deviation divided by the square root of 20. So we're going to go and just do all of that in Desmos. So in the Desmos link, I put the data for us to share. And there's our mean, 0.9652. So I'm going to write that on my paper, 0.9652. And then we're going to find our error bound margin. And so to do that, we need to get our critical Z. So our critical Z, I have a couple tabs of Desmos open, and that might be helpful for you so that you always got your just a critical Z tab open. So we're going to put in 1 minus our confidence level, and then we're going to divide by that. So our alpha divided by 2 is right here, 0.035. And when I put 1 minus that into my inverse CDF, here is my critical Z. So my critical Z is going to be 1.812 rounded. So I'm going to go back to this, and my error bound of the mean is going to be my critical Z 1.812 times my standard deviation of 0.337 divided by the square root of 20. So I do need to use my menu for that and close my menu. Okay. Okay. So my EBM is 0.1365. So step 4 is finding the confidence interval. And so to do that, we're going to take our sample mean, so 0.9652, and we're going to subtract our 0.13654, and then we're going to add the mean plus our EBM. Okay, so our lower and our confidence interval is 0.82866, comma 1.10174. And don't worry, I'm going to show you my paper. So there is our work. Here's our confidence interval, our lower and our upper. Okay. And so we are 93% confident. The SAR of cell phones in the US 0.82, we'll just round to 9, and 1.102. So like I mentioned, in the calculation of your confidence interval, you should use more decimal places, and then you can round when you're doing your interpretation. Okay, so we want to change the confidence level. What if we want to increase the confidence level? It increases our error bound, making the confidence interval wider. And what if we want to decrease the confidence level? It decreases the error bound, making the confidence interval narrower. So let's look at an example. If we go back to the delivery time of pizzas, remember we had a 90% confidence, and we were confident that it was between 34 and 38 minutes. So let's say we go back to this, same information, but we're going to do a 95% confidence. So we want to be more confident. So we're going to increase to 95% confidence. So our alpha is going to be 1 minus 0.95 or 0.05. And our alpha divided by 2 then is going to be 0.05 divided by 2 is 0.025. So we need a z of 0.025. I'm going to just, this is a common one, so I'm going to use our sheet just to give you some more practice with that. 0.025 is right here where my finger is. And so we're going to use z, our critical z is 1.96. Okay, so let's notice that when our confidence went up, and our critical z value also went up because it was 1.645 and now it's 1.96. So, so that means our error bound of the mean is now 1.96 times that standard deviation of 6 divided by the square root of 20. And so that's now 2.6296. And so our confidence interval is now 36 minus 2.6296 and 36 plus 2.6296. So we're at 33.37 and then 38.63. So it's definitely wider. So let's just go up here. So if our confidence level increases, your z of alpha divided by 2 increases, and then your confidence interval is wider. Something to think about. Okay. So let's say we were given the confidence interval and we want to find the error bound from the interval. From the upper value for the interval, subtract the sample mean, or from the upper value for the interval, subtract the lower value, then divide by 2. So it could be, and then also if you're given a confidence interval and you want to find the sample mean, subtract the error bound from the upper value of the confidence interval, or average the upper and lower endpoints of the confidence interval. Okay, let's try one. Suppose we know that a confidence interval is 67.18 to 68.82, and we want to find the error bound. We may know that the sample mean is 68, which is right in the middle. Or perhaps our source only gave the confidence interval and did not tell us the value of the sample mean. So we could do the upper, so the error bound of the mean is going to be the upper minus the lower So upper minus the lower divided by 2 to find the error bound. So we could do 67.18 minus 68.82. Make sure you subtract first and then divide by 2. Oh, I did my lower minus my upper. That's why it's negative. So it should be positive. So it's 0.82. That's one way. Or we could have taken our upper 68.82 and subtracted the point estimate of 68 and found 8.82. That's another one. Or take your X bar, your point estimate, and subtract your lower. That's one you can do too. Suppose that a confidence interval is 42.12 to 47.88. Find the error bound and the sample mean. Okay, so the error bound is going to be upper minus the lower divided by 2. So 47.88 minus 42.12 divided by 2. So that becomes 2.88. And then the sample mean is going to be taking the upper plus the lower and dividing by 2. We're going to average because our sample mean should be right in between the confidence interval. So that's going to be 47.88 plus 42.18 divided by 2. Is 45.